Welcome to my 74th tutoring session in A-level chemistry. In this video, I'll explain the molecular vibrations in IR spectroscopy. And by the end of this video, my viewers will understand as why vibrational energy levels are quantized and the meaning of overtones and combination bands in IR spectra. Here we have two atoms A and B held together by a covalent bond. The bond strength or the force constant F. Atom A has a mass of m1, atom B has a mass of m2. Now the covalent bond is not rigid. In fact, it is flexible in nature and it behaves like a spring, allowing the to and fro motion of the atoms held together by the covalent bond. Now when the IR radiation impinges or strikes the covalent bond absorbs the energy given by the infrared radiation and it undergoes stretching vibrations, and this results in variation in the bond length, where the bond length may either decrease or it may increase. So during stretching vibrations of the covalent bond, the bond length may either decrease or increase. And Hooke's law explains the vibrational frequency of the bond, where the vibrational frequency of the bond is directly proportional to the square root of the force constant or the bond strength and inversely proportional to the square root of the mass of the atoms held together by the covalent bond. So the vibrational frequency of the bond, it depends on the strength of the covalent bond holding the two atoms together and the mass of the atoms A and B. Here we have atom A and atom B held together by a covalent bond with a bond length R. So R is the internuclear distance between the atoms A and B held together by the covalent bond. When the infrared radiation with a certain energy impinges or strikes the covalent bond, certain amount of energy at a specific frequency is being absorbed, and thereby it tends to undergo stretching vibrations, and during the process there is a possibility for change in the bond length from R to R1, and there is also a possibility for the change in bond length from R to R2. Now remember, the covalent bond is not rigid in nature, it is flexible and behaves like a spring, allowing the to and fro motion of the atoms A and B held together by the covalent bond. Now here's the potential energy diagram for a diatomic molecule held together by a covalent bond with internuclear distance R representing the bond length. Now a potential energy diagram helps us to visualize how the energy of a molecule changes as the bond stretches or compresses. Now here are two models explaining the changes in the bond length as the bond stretches or compresses. One is the harmonic oscillator model, the other is the anharmonic oscillator model. Now here are the key differences between an harmonic oscillator and an anharmonic oscillator. Now the harmonic oscillator is represented by a red curve, while the anharmonic oscillator is represented by a blue curve. Now when you observe the shape of the harmonic oscillator represented by the red curve, it is perfectly symmetric and represents a parabola. And what about the energy levels in case of harmonic oscillator? Now the energy levels in case of harmonic oscillator model, they are equally spaced, And the fundamental transition that is allowed is from energy level E0 to energy level E1. So the fundamental vibration frequency of a molecule corresponds to transition from E0 to E1. E0 is the ground state, E1 is the first excited state. Now R is the bond length at energy level E0 and R1 is the bond length at energy level E1. So in order to bring about a change in the bond length from R to R1, a energy of delta E, that is difference in energy between E1 and E0, has to be supplied. And this is provided by the incoming IR radiation. IR radiation that is impinging or striking the covalent bond, held together by the, is holding the two atoms together. Now the anharmonic oscillator, it is represented by the blue curve. And when you observe the shape of this curve, it is asymmetric and the curve flattens at higher energies. Now the perfect parabola in case of harmonic oscillator is perfectly symmetric, while in case of anharmonic oscillator represented by the blue curve, it is asymmetric in nature and the curve flattens at higher energies. And about the energy levels, now in case of harmonic oscillator, the energy levels are equally spaced, while in case of anharmonic oscillator, it is unequally spaced. That is, there is decreasing spacing at higher energy levels. And what about the IR transitions in case of anharmonic oscillator? Now in case of anharmonic oscillator, the allowed IR transitions is from E0 to E2, or it could be from E0 to E3, or it could be from energy level E0 to E4. And these IR transitions that are allowed in case of anharmonic oscillator, they are usually called overtones. And later in the video, I'll give a detailed explanation about the meaning of overtones with suitable examples. Now in IR spectroscopy, we study the vibration of bonds between atoms in molecules, and a potential energy diagram helps us visualize how the energy of a molecule changes as the bond stresses or compresses. Now two models describe this vibration. One is the harmonic oscillator, another is the anharmonic oscillator. Now what is the assumption in case of harmonic oscillator? Now the harmonic oscillator is based on the assumption that the bond between two atoms behaves like a spring and the energy levels are equally spaced, and the potential energy curve is a perfect parabola. So you find symmetry in case of harmonic oscillator potential energy curve. And what are the limitations that you come across in case of harmonic oscillator? Now the harmonic oscillator, it does not consider the bond breaking or that vibrational energy levels get closer together at higher energy levels. And only fundamental transition is allowed, that is from the ground state E0 to first excited state E1. So only one transition is allowed, which is called the fundamental transition. And the anharmonic oscillator, represented by the blue curve, it is based on the assumption that real molecular bonds deviate from ideal spring behavior. and the energy levels, they are not equally spaced. And the levels, that is the energy levels, get closer as energy increases. Now when you compare and contrast the shape of the curve, both in case of harmonic and anharmonic oscillator, you'll find that the shape is symmetric in case of harmonic, while it is asymmetric in case of anharmonic oscillator. And what are the major advantages that you find in case of anharmonic oscillator? There are two major advantages. The first advantage is that the anharmonic oscillator, it accounts for bond dissociation at higher energies. Now the covalent bond, as I already mentioned, is not rigid in nature. In fact, it is flexible like a spring, and you cannot stretch the spring to infinity. At a given point of time, it tends to break. And likewise, in case of a covalent bond, at a particular point, when it is overstretched, that is the covalent bond, it tends to break. So the anharmonic oscillator, it accounts for the bond dissociation at higher energy. Now what is bond dissociation energy? Now bond dissociation energy is the energy required to break a bond. So at a given point of time, the covalent bond tends to break at higher energies. So the difference between the ground state energy level, that is E0, and the energy level where the bond breaks will be considered as the bond dissociation energy. And bond dissociation energy is the energy required to break the bond. And what is the second advantage that you come across in case of anharmonic oscillator? Now it also allows the overtones and combination bands. Now meaning of these two will be explained later in the video. Now the energy difference between the vibration states E1, E2 corresponds to the energy level of the IR radiation. So R is the bond length at energy level E0 and R1 is the bond length at energy level E1. So in order to bring about a change in the bond length from R to R1, energy equal to the difference between E1 and E0 has to be supplied. And this is provided by the IR radiation that strikes the bond that is present in the molecule. So therefore, to bring a change in bond length from R1 to R2, IR radiation with the energy of delta E is required. Now this delta E, which is the difference in the energy level between the ground state and the excited state, it is specific for a given bond. And that is how you see the stretching bands at different wave numbers, because this delta E is specific and different for different bonds within the molecule. Now what are overtones? Now the anharmonic oscillator, it allows overtones and combination bands. Now what are overtones? Now these overtone peaks occur when a molecule absorbs energy equal to a multiple of the fundamental vibration frequency. So usually it is twice or three times. And what is the cause of this overtone peaks? Now, although vibrational transitions ideally occur only from the ground state to the first excited state, transitions to higher vibration states like E2 and E3 is also possible. but the intensity of the peak will be very less. Now, for example, if a carbonyl group stretches when the IR radiation impinges or strikes the double bond holding the carbon and the oxygen atom. So if a carbonyl stretching vibration appears strongly at 1700 centimeter inverse, an overtone might appear weakly near 3400 centimeter inverse. That is twice its frequency. So 1700 into twice will give to 3400 centimeter inverse. So in case of cyclopentanone, now here's the IR spectra for the compound cyclopentanone. And in case of cyclopentanone, you see a small absorption band at 3462 centimeter inverse. And in fact, this particular peak is the overtone of the carbonyl stretching, which is occurring at 1731. So the fundamental vibration for cyclopentanone with respect to the carbonyl stretching, you see a peak at 1731 centimeter inverse. And this peak at 1731 centimeter inverse is the fundamental transition allowed, which you generally see in case of IR spectra of cyclopentanone. And in addition, you will also observe a peak at 3462 centimeter inverse. That is to say, you see a overtone, and this overtone is seen at 3462 centimeters, which is twice that of 1731 centimeter inverse. So this will be a very good example to explain how overtone peaks occur when a molecule absorbs energy equal to a multiple. Usually it is twice or thrice, but here in this particular specific example, it is twice of the fundamental vibration frequency. So the fundamental vibration frequency in case of carbonyl stretching for cyclopentanone, you see a peak at 1731, and because of the overtones allowed, you see a peak at around 3462 centimeter inverse. And what about the combination bands? Now, combination band usually results from the simultaneous excitation of two or more fundamental vibrations. And these bands appear when the energy of the absorbed photon matches the sum or difference of the frequencies of two vibrational modes. Now, say for example, if a molecule has two vibrations at 1200 and 1300 centimeter inverse, giving rise to a peaks at these respective wave numbers. You might also observe a weak combination band at 2500 centimeter inverse. Now when you sum up 1200 and 1300, you'll end up with 2500 centimeter inverse. So you see a peak at 1200, a peak at 1300, and there is a weak combination band at 2500, which is sum of the frequency of these two vibrational modes. Now to mention a specific example, now in case of all the amino acids and their respective salts, you will see a characteristic band at around 2100 centimeter inverse. And this weak band at around 2100 centimeter inverse is the combination band, which is shown by all amino acids and their salts. Thank you so much for watching my video. I hope you enjoyed it, and I'll meet you in my next interesting tutoring session.